Alright, time for another draftphysics.com, debatephysics.com also, but yeah, they just won't counter-argue what I can assert. Okay, the evidence kind of obviously shows and demonstrates and proves, and they really don't have any counter-arguments. They really can't show you it taking 25 times the fuel to spin something 5 times faster, or even to accelerate something or to give something a velocity that's 5 times. Nor can they show it doing 5 times the, or 25 times the work. Something going 5 times as fast, doing 25 times the actual physical work of moving matter. And that's what work is, and that's what energy is, and that's what momentum is matter, mass, moving. Not mass moving squared. Anyway, part of that, okay, part of the silly conversations that physicists like to have is this subject of gravity, where they'll claim that gravity isn't an action, okay, that it's actually an accountable bit of energy in the universe. It's creating, generating, and it can't just be blamed on some bent geodesic, because there's no way to put energy back into whatever the bent geodesic is. There's no way the heat that radiates out of any body that has any mass in the universe, anyway, that radiation that is being created by gravity, is accounted for as somehow being converted into something called a bent space. It just isn't. There's no mechanism for it. And, gravity does everything you need to do to be a force. It quacks like it walks like it has feathers like it does all of it. And there's just no good reason to deny what is obvious, that whatever is causing gravity, it's really giving things motion, and it's really causing a change in their motion, and it's a real consequence. The rest of the universe isn't moving towards something, okay? It isn't accelerating in the opposite direction. So this is almost as bad as the argument where they claim the Earth is constantly accelerating upward, and somehow the universe is in some way constantly getting bigger or something, and we're just too stupid to understand. Yeah, no, they're too stupid. And they just talk crap, and it's really, I mean, it should bother people of intelligence that they're being patronized, in terms of being told absolute fairy tales and falling for them. I mean, it's just so bad. Um, so she even, in some of her videos, she's used crazy Muslims and different things as examples of, people off the rail, reasonable. And clearly, physicists are way off any kind of rational rails. They just make up all these invisible, wooey mechanisms to describe what are kind of simple mechanisms. So again, they've perverted concepts like just photons now are waving, but they're not waving. They're particles, and there's some sort of, they can be in two places at once, and they can be two kinds of things at once, and it's all just nonsense, because they're not smart enough, okay, to get the right answer, and so they just come up with any kind of silly nonsense and convince a bunch of people that it's true. So they've gotten everything wrong. There's no entanglement, okay? There's no superpositions. There's no singularities. All of their rhetoric, all their quantum crap is just that crap. They haven't got any of these basic subjects correct. They don't know what matter is, they don't know what energy is, and they don't know what space is. We don't have the right answers. So anyway, she did this video on gravity about a year ago, and it says gravity is not a force, but what does that mean? It means you're crazy, silly. It means you have some delusions and notions in your head that just corrupt any capacity to see the real world as it is. because gravity is so obviously energy producing, and only a force can produce energy. Force is energy. Does it have to really be explained? It's motion in something discrete and small that ends up giving big things motion. It's the whole Newtonian idea, the Descartesian idea, that the motion is conserved in the universe, and that you can be moving little air molecules, or you could be moving elephants, or you can moving electrons and protons through a wire. I wonder if she thinks Veritasium's notion that induction is what makes electricity work, rather than actual physical electrons pushing through a wire. Alright, anyway, so to the video and such, and so forth and whatnot. I mean, maybe I should just play all her videos and critique them, but most of them are on nothing subjects. She doesn't really talk about these the elemental subjects, certainly not much about wave-particle duality or kinetic energy, but she does talk here about gravity, so at least we can get to something elemental and just demonstrate how silly her arguments are.
This video is all about Albert Einstein. Yes, that guy again.
That crap again, frankly. Look, Einstein, I'd love to like him, but, hypocrite, okay? Calls other theories spooky action when his own theory of bent geodesic is as spooky action as you get. A non-mechanism creates motion. Something without any energy makes things have energy. Makes energy in the universe. I mean, it just breaks any notion of conservation of energy, and it should have been obvious to everybody that it did. But what wasn't obvious to people is they didn't recognize that the Earth's center is molten because of gravity, that the sun is radiating photons is really hot because of gravity, that gravity makes things hot. And as soon as you recognize that simple truth, that the force of gravity, the mechanism of gravity, is making the universe hot. It's creating a bunch of radiation in the universe, and that you have to account for that. And it's clearly going to create enough that actually created the force in the first place. The force that pushes the matter together and creates the pressure and the heat has to equal, the amount coming out. And once you recognize that fact, then you recognize the universe is full of this pressure coming out of other objects that are the same thing that's going to compress it. The Earth is being compressed by the rest of the universe, and the Earth, in a sense, adds its contribution to the compression force. The universe is a very high-pressure environment. Yes, empty space is empty, but it's full of quanta of force in the form of radiant energy. Photons, for example, all the varieties they come in, including the variety that we can't pick up on our radio receivers. The variety that doesn't have a frequency that we can tune into.
Einstein is...
Dentist. Sorry, unfortunate. Alright, so she says is famous for his theory
of general relativity. It's taught us that gravity is not a force.
So he has two theories, special relativity and general relativity. In special relativity, it's about a velocity. In general relativity, it's about being in this field of gravity. And the argument I would make is the field of gravity is an extra velocity. And that's why in heavy gravity, you are more time dilated. So the trick is that the satellites going very fast aren't the things time dilated. There they have the clock that's going too fast, not too slow. So the irony is The clocks on the ground are the ones going too slow. They're the ones more time dilated, because the fact is they are pushing in and out of the gravity constantly. They're constantly pushing in, the ground pushes them back out. They're oscillating in the gravity. Obviously this is a lot more distance than this. Straight line, very short distance. Jagged line, lots of distance, meaning your velocity is a lot higher, technically. Your actual movement of matter is more ground covered.
And that's probably the most misunderstood physics fact ever.
Well, it'd be nice if you had an actual quote from Einstein saying gravity is not a force. Okay, that it's not one of the four forces as they call them, but there's really just this. There's not four forces. There's only one force. And the fact is you can have the force in different patterns. I can hit you with bullets going bang, 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 or I can hit you with bullets going bang, bang, bang. Or I can hit you with bullets going bang, 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 right? And all those three, one of them you can't hear, you won't see, you can't receive on your radio because it's not a standard frequency. And the other you might see as blue light, and the other one you might see as red light. So, and then magnetism would be another form of pattern, okay, that's being emitted by an object. Magnets don't make things move, okay, for free. They're not creating their own force and throwing it into the universe. They don't generate any kind of motional energy. They're just reflecting the field that's hitting them, and in that reflection, okay, just like I'm just reflecting somebody else's, I'm reflecting this light bulb's energy at you. That radiation is the radiation you see, okay, and I didn't generate it. I just absorbed it and reflected it. And that's what everything in the universe is constantly doing, is absorbing and reflecting. They're at equilibrium. They can't absorb perpetually, so they're constantly emitting essentially as much as they've absorbed. And there's just a bit of a delay between the stuff coming in and the stuff coming out. But I don't know if I can think of any quote offhand where Einstein made any direct statement about gravity not being a force, or not fitting the profile or suitable definition of a force.
Like, even physicists get it wrong all the time.
And you get it wrong, so yes. I mean, it's just... So what would the physicists getting its wrongs arguments would be the obvious ones. Okay, that the Earth's surface is not motion. It is not moving us, in the sense that we first have to push into it. So you could just make the simple point that if I have two surfaces this way, okay, there's no friction. The only way you create the friction is to push one into the other. Right? That's what has to happen. One has to have a force pushing it into the other one before the other one can push it back out. This one doesn't push this one away before this one makes contact with it. And so, like, if you doubled the Earth's gravity, all of the friction would double. It would pull energy out of objects twice as much, twice as fast. That kind of obvious stuff. So obviously it's not about the Earth's surface that's causing the objects to have motion, and it's certainly not about the Earth's surface that's causing the Earth to be under pressure and to be melted, mostly. Most of the Earth is melted. It's so hot. It's so hot with the conflicting pressures coming from both sides in all three dimensions, and constantly pushing and pushing back and pushing and pushing back. Constantly. That's called heat.
Gravity is not a force, and since that...
So, okay, let's count how many times she says that, right? Let's try to count. It'll be too many times to actually count, but we'll put a notch for every single time she propagandizes so aggressively for this point that she says this line, I think it's more than 50 times in this video.
There's no force pushing down on you. That means you're currently accelerating upwards.
So we're not currently accelerating upwards any more than we're currently accelerating towards the center of the Earth. So it's kind of, I think, just an undeniably rational observation to recognize that, yes, the thing getting pushed is our electrons and protons. We, as the collective object, are not getting pushed. That's why every single mass, no matter what size it is, falls at the same speed, because it's collecting the force based on its mass, the size of its mass. So if you have a big mass, you collect lots of force, big sail, lots of wind, small sail, only a tiny bit of wind. And it's all moving into the Earth, and the Earth, you have to actually contact the Earth to be pushed back out. If you don't contact the Earth, you just keep getting more and more velocity. Nothing slows you down. There's no pressure in the atmosphere pushing you back up. The atmospheric pressure is pushing you from all sides.
Unless you're watching this from the ISS, in which case, please say hi to the moon.
Whatever that is. They're not very close to the moon, relatively speaking. They're 0.0000001% closer to the moon.
How does gravity work if it's not a force?
So again, it has to be a force because it creates real energy in the universe. So the gravity is what heats objects, and it's obvious how it heats them, okay, in the sense you could just think about it for a very small amount of time and understand that if the force is in the universe, the pressure pushes in both sides, and you can never cancel the energy, all right? The energy always has to go somewhere. Well, if it's stuck trying to get pushing through each other, that's what it's doing. That's the heat. The heat is the fact that it takes time for the energy to push through all the counter pressure from each other to get back to the outside and be fast again. So it's stuck, moving, jiggling the matter, and that's the heat that melts the Earth. It's why it's hotter in the center than it is the further you go out. It gets cooler and cooler because there's obviously a lot more mass to have to jiggle.
That's what we'll talk about today.
And it'll be nonsense, and you'll just arrogantly pontificate, and you have zero reasoning and rational evidence to defend this nonsensical proposition that gravity isn't in every way the definition of force in the universe.
An accelerometer is a device that measures acceleration.
So when I first saw this, I said, well, why are you showing this? Why don't you just show a spring? Okay, because acceleration is just weight. You're just talking about contact force. You're talking about the pressure of contact. And that's what accelerating is. All right. And you can't move something in the universe without, and for us, pushing on it. We don't have ray guns. You know, we don't have gravity guns. We don't have force fields. We don't have tractor beams. We don't have any of that stuff. So for us, it is basically, you know, you have to shoot something at it that we can see, like photons, something physical.
If you'd hold an accelerometer steadily in your hand, it'd tell you it's accelerated upwards.
No, it would tell you it weighs something. Okay, so the only thing it's going to measure is how much it weighs. The more I put on top, the bigger I make this circuit board, the heavier I make it, the more acceleration it'll read, because it's just going to read the difference in the pressure of the contact. And that's it. It's not that complicated. I'm just going to basically read the accelerometer's mass. We're just talking about how heavy does the thing get. That's what an accelerometer is telling you, is how heavy is something, and how heavy something is how much momentum is there. So again, this is a, where did I put it? Yeah, the spring, the scale. All right, guess I put my accelerometer away, the scale. Anyway, you compress the scale. You just turn it sideways after it's been compressed, lock it, and then release it, and you move something with momentum. Clearly, it's momentum that it's measuring. And what it's measuring is a contact force. Like two things could have a relative motion in these directions, but they don't hit each other. Their vectors don't intersect. And I can give one of them another velocity in another direction because it's a material object. It can move in more than one dimension at a time. And it could be moving, and then it's getting pushed into the other object, and then it rubs, and there's friction, and it exchanges its motion with the other thing's motion. The two of them compare. This one could have $5 of pressure, and this one could have $45 of pressure. This one could have 0, and this could have 45. And as they contact, the 45 gets diluted into the other object. They start sharing the pressure, sharing the motion, the quantity of motion, to go back to Newton's perfectly rational description of the reality.
This isn't hypothetical, weird, theoretical physics.
Yes, it is nonsense. It's absolutely religious, baby talk, mushy, silly, made-up crap. Okay, you're not being intuitively gullible, okay, to fall for the idea that the obvious thing you see happen is what's happening. Something gains velocity until it hits the Earth. How does the Earth know? Oh, it fell 45 feet, so I will push up to it really hard and smash it to pieces. How does it know that it's supposed to hit something that falls out of the 100th story of the building, and it hits something coming out of the 30th story? How does it know that one of them has more velocity than the other one, and it's supposed to push harder and get to it quicker and smash into it? Yeah, that's silly. It's absolutely silly. It's as silly as 25 times the fuel to go 5 times as fast. And yet they preach this crap as if it has something to do with reality, when it has nothing to do with anything real. And you human garbage fall for this crap. I mean, don't you know what a fool and a sucker is? Have you ever watched the W.C. Fields movie? I mean, go watch one, okay, and find out what being a dupe and a fool is. Because you're fools.
Talk. You can buy one and just see what it's.
You could, again, you don't have to buy one. You can find a spring somewhere in your house. There's a spring. All you're measuring is the differential. The fact is the thing pushes in first. The spring absorbs the energy and tells you, okay, I got that. And the Earth doesn't have the same exact pressure because the spring stored a little bit of it. And that's all it's doing. So the gravity keeps pushing, so the spring can never bounce back up until you get the mass off of it. But it's showing you the differential, that the pressure from below is after the pressure from above.
Says. This is an example of how the reading of an accelerometer looks like when it's lying still on a
I mean, this tells us something. I mean, can't you just say, okay, well, I can't put a graph on here that gives you some sort of, what is this, acceleratons. Yeah, this is your acceleratons. Oh, this is such crap. It's your weight. It's just weight.
Table. It tells you it's accelerated upwards.
It's just telling you how much something weighs. It weighs more the more it moves. I push an elephant into you at 1 mile an hour. It weighs 1,000 pounds, the actual weight of the elephant, because 1 mile an hour is about the right speed to duplicate what gravity creates. And if I push the elephant at 2 miles an hour and let it hit you, it's going to read a higher acceleration, right? Twice the acceleration. Yeah, not complicated. You're just measuring weight. An object can have different weight based on how fast it's moving. mv is its weight, is its momentum, is its energy, is its force, is its capacity to do work. They're all the same thing. Is its thrust.
And this is entirely correct. If you hold an accelerometer still on the surface of Earth, it's indeed accelerated upward.
No, it's not. Okay, so it's indeed not. It's just measuring the differential in the mass, the force of gravity, because the accelerometer has a mass, and if you put a bigger mass on top of it, it'll read a bigger and bigger number. It's just weighing the objects. Okay, it's telling you how much force are you collecting, and that's it. And how much force are you applying that eventually goes into the Earth.
Why does that surprise you? If you hold something on your hand, you feel that it's pressing against your hand, downward.
Right, and if I put it a millimeter above my hand, I don't feel a thing. Because the Earth doesn't move, the pressure doesn't push up and keep pushing and keep pushing and keep pushing. The thing that keeps pushing isn't the Earth coming back up, is the force of gravity pushing down. It's a push-averse, by the way.
It's like when you're trying to accelerate a car with your hand. It'll push against it. If you hold something in your hand...
It's just about pressure. Pressure's created by conflicting momentums. So two things can't push pressure on each other unless, okay, there's something between them, like in electrons and protons, force, bits of bullets bouncing back and forth, or they have to make contact. They have to share their difference, okay, and they have to share it through contact.
That's not the gravitational force pushing it down, because gravity isn't a force.
So there it is again. Okay, mark that down. Yeah, I really probably, it's probably going to be very unrealistic to stop and mark it every time. Yeah, I should count them ahead of time or something.
It's pushing on your hand because you are accelerating it up.
So that doesn't happen, right? So again, it has nothing to do with you accelerating it upwards. It has to do with you making making contact with your hand and first pushing it down, increasing technically the pressure. So if I have a balloon and I push on it, I expand the balloon. Okay, if I change how much volume. Okay, by taking some of the volume out of the balloon here, I expand the balloon over there. I increase the pressure. I can't expand the balloon without increasing the pressure, and the increasing the pressure is what pushes you back out.
Upward. Why is the thing in your hand accelerated if you don't move your hand? It's because you are accelerated. And
so again, more nonsense. You're only accelerated in one direction. Look, all this comes down to the notion that they don't understand that gravity is moving your electrons, not you. Okay, your electrons and protons. Your actual physical matter, the stuff that makes your atoms, that's the stuff that's actually collecting the force. And it collects it in this quantized way where every electron collects the same amount and every proton collects the same amount. So it ends up being just how many electrons and protons do you have, and that'll decide how much you can collect. And it moves through you because it's a force, okay? It's a very discrete and tiny mechanism. It moves through you and pushes all of you almost at the same time. I mean, there's probably some difference. The top of your head force does hit the top here, and it probably does have to force through conduction through to the rest of you to some extent, but it's not nearly as bad as atoms. So I think this is probably a point that's important enough for me to draw. So I will do that. All right, drawing mode now. Yeah. So the difference between us pushing on something was what's happening. So here's a surface and it's full of atoms. Okay, and the atoms have what we know are this rubbery connection to each other through the electrons. All right. And the difference would be is that gravity, okay, is going to be affecting something based on the actual little bits. So the atoms no longer are relevant. There's no, it's just the bits of electron and proton, and the force hits, and it's just really about them hitting all of those things. Where the Earth, when it pushes you back up, so you're getting hit by a force that's very discrete and goes right through you, hits everything, pushes everything down. And then when you push back up, though, you're pushing on individual atoms. You have to go through the electrons, okay, on the outside of the atoms. You have to create a bunch of jiggling in the atoms. You have to get the atoms to communicate. And this is very slow. This is, the force moves, at the speed of sound inside the medium kind of thing. So it takes a while, very slow, for the force to transmit from your feet to your head. And that's why it's got all this rubberiness in it, because all of these atoms are, electrostatically, magnetically readjusting their positions to accommodate this pressure that you're pushing on the atoms. So this is incredibly slow compared to the force that pushed down, which was incredibly fast. And your nerves are basically, when you feel something, it's really about two cells being next to each other and whether or not they move relative to each other. And if they don't move relative to each other, you can't feel your motion. You can only feel motion when some irregular motion happens, where one part of your body moves more than another part. That's how nerves work. There's no signal from the nerve. If I move this exactly the same as I move that, then my nerves aren't going to notice anything. So we don't notice getting pushed by a force that goes right through us, like magnetism or charge, or if we're moved by it. But forces that first have to heat our surface or do something where they can't push right through us, we're going to feel those, because there'll be an unevenness in our motion, an unevenness in our receiving of the pressure. So the force of gravity is benign in terms of it's invisible. We can't feel it, but it's happening. We're being pushed. The electrons and protons are aggressively being pushed. Okay, we can't sense it, but we can surely sense the push back from the earth, because that one has to go from our feet to our head, or from your ass to your head. Anyway, simple enough. All right, back to the story, the fable as told by. Is that the one I want? Yeah, apparently. Something seems wrong there. I don't need this. All right, leave us continue.
You are accelerated because there's a force pushing on you from below.
Right, and that force is less than the force pushing you from above. There's a constant deficit between the two forces, and you can just see it from this image. The ground pushing up, the force on the other side of the universe, that would be a balance technically, over time would be a balanced amount of energy pushing from one side to the other, in one direction and the other, has to go through the earth, okay? And that's not going to be as fast as the stuff going straight down out of the universe. Open to the universe, there's no obstruction between me and the universe. If I put an obstruction in the way, the force isn't going to be able to get to me at the same time. It's going to have to first be absorbed and then radiated. And the time delay is what's creating the differential called gravity. And the time delay can be understood. You can see the spring compressing, so to speak, in the form of the molten center of the earth. That's the consequence. That's where the energy is that's supposed to be keeping you from moving. The energy that's supposed to be keeping you from moving is melting the earth instead.
It's the floor, or rather the atomic bonds in the floor and in the ground below. You see, the entire earth has internal pressure.
This is the hilarious part. And where did it get it from? Where is the pressure from? So every one of these out arrows, you could just draw it as an arrow that went in over here. And it's going out over here. And this one went in over here and is going out over here. So there's, she's missing the obvious in arrows, okay? So there's, for every out arrow, there's an in arrow. And the only difference between those arrows is one set of them moves at the speed of light, the ones that would be going in, and the ones coming out have been retarded by the fact that they're pushing matter. And when they finally get to the surface, then they can be released as radiant energy. They can be converted back into free force moving the speed of light. So there's a ton. The same amount of energy went in is the same amount of energy coming out. And there's just a delay that has heated the Earth. That's the simple explanation that is a challenge to their wacky woo theory. All right? And I don't think there's any way to deny it works just fine.
Otherwise, it'd collapse.
And again, but why is there the pressure? Why would it collapse? What is the mechanism causing it to be collapsible? What is the force trying to collapse it? Yeah, gravity. Yeah, that's right. Duh. There's not some other mechanism. The Earth is hot, meaning it's full of jiggling, and it wants to jiggle the jiggle into the universe. And it can't do it because there's more jiggle coming in.
That pressure generates a force on everything on the surface. And as Newton taught us, a force creates acceleration.
And, Newton didn't teach us. Newton observed and described would be a nice dignified way of explaining what Newton did, is that he observed and and he did it reasonably and rationally, and he didn't come up with wooey answers.
So that pressure of Earth creates a force which accelerates you on the surface.
Again, the force pushes the Earth, the matter together. The matter would, okay, if you organize it well, if you organize all the electrons and protons well, they can be very, very small space. But the trick is they have to be organized and arranged. And getting them into that arrangement is the hard part. Getting them to fit together, okay, coherently is the tricky part. So it's like putting a puzzle together. If you don't put all the pieces together the right way, you have a bunch of air spaces, right? If I just take the puzzles and push them together without putting them, the right pieces next to the right pieces, I'll end up with a bunch of errors, and I'll end up with a bunch of wider and wider and wider space it takes up. And that's the problem with the atomic bits, is it's hard to get them in the right positions. But if you do, like creating a neutron star, then you can have a lot of atomic bits in a very small space. And you'll have less heat.
But wait, you may say, there's also the gravitational force pushing down. So
there is the gravitational, also or not.
So the two forces balance to zero, right?
On the surface, they do. That's right. So the surface is 9.8 meters, but that's the surface pressure, and the point is that it can't push on you once you're off the surface, once you've left the surface matter. So every bit of the surface matter has to be going 9.8 meters per second. And so yes, that's the amount of pressure pushing out, okay, at that point, because it's balancing the pressure pushing in. It's balancing the gravity on the surface. So the surface will always be where there's a balance between the gravitational force and the differential you're creating.
No, because gravity is not a force.
Gravity. Say it again. Yeah, that's only 3 so far, but it seems like hundreds.
Gravity is a consequence of moving in a space-time that's been curved by the presence of masses.
So what nonsense? Says them, okay? Says them. The consequence of moving in a curved space-time, whatever that is. So I think when Einstein was challenged to actually say, what the hell is this stuff, he conceded, well, it must be an ether. Yeah, sure, go ahead. Call it an ether because I can't deny it. Obviously, it has to be something that's bent. I can't bend nothing, so it must be something that's bent. So this is all just sort of bullshit. I mean, and again, it can't be this idea of a curved space-time. It's really calling it a convergence. That's what it is. when they teach it, they use mock gravity. So Leonard Susskind, when he teaches relativity, he basically creates a scenario where you have a convergence of water. So he uses water as an example, and a flat plane, because he can only do it in two-dimensional. But three-dimensionally, it's doing exactly what the sun is doing with photons. So it's the same exact mechanism. The sun shoots photons out of its spherical mass, and they're spreading in two dimensions as they come out of the small sun, relatively speaking. They come out of it and they're spreading in two dimensions. That's the inverse square law. So gravity is doing exactly the same thing. The force in the universe is doing exactly the same thing when it's pushing in. It's pushing in by the inverse square law. There's a whole bunch of stuff here, and it's shooting into every single object in space. So I put an object here, it's going to look like, from the object's perspective, looking out at the universe, it's going to look like all the photons are out to get him, because he doesn't see the ones that miss. So he thinks, wow, they're all trying to hit me. And everybody has that perspective that they're the focus, okay, and they're getting hit from all directions by all this stuff, somehow knows they're there. And all they really are is just in a position in space, and every position in space has got a ton of photons flying through it all the time. A ton of energy. So any piece of matter put there is going to have to absorb and reflect a ton of energy. Right, there's no space-time. There's space, which is the black stuff there, okay? Nothing. There's distances, there's places in that space. Then there's this little stuff moving the speed of light, okay, in straight line vectors. And then all I have to do is draw in here somewhere electrons and protons. All right, and then that's the story. There's nothing else to the story. There's just the bits moving the speed of light, electrons and protons. And the bits have to stick to an electron or proton to move it. And so a bit going the speed of light, when it's pushing an electron, it's going something less than the speed of light, a lot less than the speed of light, I would assume, in most cases, except when there's a lot of bits of force the bit has collected. It's like just collecting a Sisyphus. There's boulders, and then there's Sisyphuses. So little tiny Sisyphuses stick to the boulder, move the boulder. The boulder moves slow. The Sisyphuses, when they're free, when they're not bound by some boulder, they move very fast, the speed of light. Very fast relative to us. But that's the universe. There's no there's no space-time in there. There's just electrons, protons, space, and force. That's it. Everything else they just made up. It's crappy, wooey fables. Hobgoblins, Smurfs, SpongeBobs. It's a cartooniverse.
If there are no masses nearby to curve space-time...
So it doesn't curve space-time. All of those silly drawings of bent fabrics and everything else are relying on gravity to illustrate how gravity is created. So they're explaining how gravity is created by... It's like saying this is how a duck is created, by showing somebody an egg. That's not how the duck was created. It's just cheating.
It's flat, so long as there's no force acting on an object in this flat space-time.
So again, there's absolutely no place you can go in the universe where this crap isn't flying through the space. So you're stuck, always being stuck in a place that's full of this energy. You can't escape it. You can't escape the pressure. You can't escape the entanglement. Because some of that crap is going to reflect off of you. Just a fact. And that's your signature. That's defining where you are and where you're going.
The object will move in a straight line. If there are masses nearby, space-time will curve.
So space-time will curve and somehow give the photon, this one-dimensional object that moves only in one direction, a second momentum. So the photon will be going this way, and the photon will be going that way, which photons, energy, force can't do.
And the object no longer moves in a straight line, even in the absence of a force.
So again, even in the absence of a force, there's no absence of the force. The force is always there, and all you're basically saying is yes, when you get near another mass, the fact is the force has to go through that mass to get to you. And that takes time, so there's always going to be a little differential between the force that doesn't have to go through matter and the force that does have to go through matter, obviously.
The usual way to
So this is just a horrible illustration because this doesn't work because it has friction in it and it ruins the whole thing. Because the truth is that things won't go into orbits. They'll either crash directly right into the center or they'll fly back out. That's the only two choices there are. So anything going over this edge has to come right back out again, or it crashes into the center. It never orbits because you have to change its speed for it to orbit. So it's a terrible example. It's not physically accurate. It's just deceptive. It's not illustrating the real fact that it's a convergence. Okay, so it'd be better to be pouring water over a curved surface and then play this game. But again, you're still stuck with friction.
explain this is with a large marble on a rubber sheet that deforms the rubber. This is an analogy for how, say, a planet curves space-time around it, and then another smaller marble, which
and
seems
it's just really bad analogy. So again, they gave it the motion in this direction. You know, nothing just happens to fly, get into a gravitational field, just poof into it with a direction. So that never happens. So if they did it honestly, that's not how it's going to move. The fact is if they throw it in a straight line, okay, coming in on a straight line, it has to either fly out the other side or crash into the center.
to be attracted to the bigger one. It's a pretty good visualization.
It's a piece of crap.
It's just that you shouldn't ask why the big marble bends the rubber, then it gets really confusing.
No, what you obviously can say is this is a silly two-dimensional drawing of a three-dimensional object, and it's just too flat. It doesn't show the real thing. The real thing is a convergence. In 3 dimensions, there's a convergence. It's just a denial of the obvious, that it's just the sun in reverse. The photons coming out of the sun are exactly how, if you could reverse their direction, that would be gravity.
So in this curved space-time around a planet, if there's no force acting on you, you fall towards the planet.
So there's no force acting on you, yet you fall towards the planet by the magical mechanism that gives you velocity, and 9.8 meters for at least a few miles anyway. So yes, it's essentially still 9.8 meters for the astronaut floating in space. And the fact is the gravitational effect is going to be every second he's going to gain 9.8 meters of velocity in the downward direction. Now the catch is he has to have a huge velocity going sideways to keep pushing him in a different angle as he's falling. So he keeps falling at a different angle, and that angle ends up being exactly the opposite of the angle he started with. You can sort of see it. And so it all compensates, and he can't gain any velocity because he starts opposing his orbital motion is opposed by his gravitational motion eventually as he falls. The wrong thing to hit. I'm going to hit this button.
That's not an acceleration. But if something gets in your way, like the surface of the planet, then that creates a force. So now you're...
So you know that the force you hit the Earth with isn't going to be 9.8 meters per second. It's going to be what you've accrued, what you have collected, falling for some distance. So the Earth can't possibly know, okay, the Earth is sitting there saying, okay, you're falling from this height. I only hit you a little bit. you fall from this bigger height, I hit you really hard. I mean, it can't know any of that. So it's just a silly cheat of the reality. That it's clearly a collected force, because clearly you can hit the surface of the earth with very different amounts of momentum. There can be a very different amount of conflict in your velocities. Okay, so the longer you've fallen, the more seconds you have fallen freely, the more force you have collected, the more momentum you have collected, the more difference in your velocity versus the acceleration of the surface of the earth, there's a greater and greater difference. And you'll hit with a very different amount of impact.
Accelerated. This is why there's no force pushing down on you right now.
So she says, no force, there's no force. When of course there's a force, of course.
There's only a force pushing up.
So again, more nonsense. You can't feel the gravity pushing you down, you feel the earth pushing you back up. That's all there is to it. And you can understand why you can't feel the gravity pushing you, because it's pushing every single part of you the same speed at the same instant. All the pieces of you are falling at the same speed. I can't feel the difference. And obviously when the ground pushes back up, yes, it's pushing your feet first. And there's a huge difference between the time your feet are pushed and the time your head moves. A gigantic difference, and the whole difference is you're also a springy thing, and so you don't even move as a rigid body. You end up absorbing a ton of the energy. So your head doesn't even get to feel a tiny percentage of the energy, because your body absorbs it.
If you took away the surface of Earth, you'd fall. And if you
and yes, and the trick would be, right, so if we do that example, so maybe I'll draw that one. It might be worth it. Okay, back to drawing mode. All right, so if I was to create a circumstance where I could fall, okay, through the earth, okay, so let's just put a hole in it, all right, and then I can fall through it, okay, so I can experience the gravity, and but I will never have contact with the earth. So I'm going to fall equidistant from these sides. Obviously the mass on both sides is going to be the same. The gravity is still going to affect me because all these angles are still in charge. So yeah, the force is negated coming up from the bottom, right? This part doesn't have to go through the earth to get to me. So the force directly coming down is going to be the same as the force coming directly up. But all of these angled forces, okay, are still in play, and all of those are still going to accelerate me. Now, as I get deeper and deeper, the acceleration is going to get less and less, okay, because there's less and less mass this way absorbing the energy. So at the full, when I'm right here, just about ready to enter the earth, so I have, let's say, 50 miles an hour. All right, that's how fast I'm moving when I go right into the earth, 50 miles an hour. This force is still pulling me, so I'm going to still gain acceleration, because there's still a difference between the force pushing me down and the force pushing through the earth. So I still have a differential, so I'm going to gain more. And so let's just say the more is going to be at my peak. It's going to be 100 miles an hour as I pass the center. So I will fall, and I'll just keep gaining momentum, gaining velocity. I'll go to a peak velocity there at the center, and now the system's working in reverse. Now when I'm moving out, okay, I'm the differential is exactly the opposite. And so now this side is absorbing, and so now there's more pressure pushing me this way, so it starts decelerating me. But the fact is, I'll pop out the other side 50 miles per hour. All right, and I'll go up a little bit of distance, whatever that would be. At 50 miles an hour, you'll go a certain amount of distance, depending, and I'll oscillate forever. So I push you into the gravity at 50 miles an hour. You go in, and then you just oscillate forever, because there is no cancellation. There's no force disappearing. It always has to go somewhere, and as long as you don't make contact with anything, you can't lose the force. So as long as you don't make contact, the force is conservative because it's a sphere. And it's always going to be the same amount of force going away as there is going towards. And so you'll just sit there and oscillate back and forth forever. You can't say that's not a force. You can't say a force isn't creating that motion, because the force did. And the initial force was you going in. You going in is the initial force, and frankly, it never goes away. Yeah, simple enough. I mean, this is 5th grade. You know, 5th graders, you know, whatever, 12 to 15-year-olds should be able to understand this. All right, back.
Well, there'd be again no force acting on you. This is also why the Earth would collapse if it had no internal pressure.
So again, and it would have no internal pressure if there was no gravity. So the internal pressure is directly a consequence of the gravity attempting to force the electrons and protons together, and they can't self-arrange in some simple way. They end up pushing on each other, okay, and creating a tension that doesn't allow them to just automatically stick together perfectly and eliminate all the extra space. You know, just perfectly get to the right distances from each other to balance each other's tension. It's complicated, and it's especially complicated when they're already in the form of atomic nucleuses. They already have an arrangement, and that arrangement has to be subtly broken to make two things fit together. To make a new compound, you often have to force the issue. You have to break pieces off to force the issue. Might be worth showing the simulation. Yeah, I might as well throw it in. Alright, so this is the real only universe. So this is where you get to things that there's nothing else. There's nothing else smaller. There's nothing else more elemental. It's just these little bits of force moving the speed of light, technically. I would argue. And that mouse should show up. And then matter bits, okay, electrons and protons. And the fact is, when they arrange, so let's just read. I think I can get away with this. Yeah, redo it. They're in disorder, and they now have to find their order in the middle of this force field. And the fact is that their red will bang into a red, and that's not going to be allowed. And a green will bang into a green until they find the right arrangement, and then they'll do exactly what you would expect from magnets or elements of charge. They will, the dissimilars will attract, the similars, the alikes will repel, and they'll have to find a balance between those forces. And the balance will be some kind of geometry. So it's looks like this now as 3 different units, but eventually they could all combine. They could make a string of red, green, red, green, red, green, or they could make a box of it or a circle of it. They'll create different geometric relationships that maximize the amount of red to green, okay, and minimize green on green and red on red. And that's what the universe is doing. That's the real universe. The one we're just an emergent function out of. Everything that we do, they do it first. The electrons and protons have to move first. Really important to understand that. It really is important. Alright, back to the video.
It's not because there's a gravitational force acting on the matter, because gravity isn't a force.
There, she said it again. So again, she just keeps saying it when it has every aspect of being just like photons coming out of the sun. Every element of it screams that it is made of something, okay, and that there's a difference between the somethings. The something coming out of the earth and the something coming out of space. There's a differential, and that's what you're stuck in.
It's because without internal pressure, stuff would just freely fall in the curvature.
So whatever that means, freely fall in the curvature, not acknowledging any of the physics, which is charge, the fact that atoms repel each other, the fact that, that they only combine if they have a connecting point, a positive to a negative circumstance where they can find a place to connect. All right, but generally speaking, they don't.
That it itself creates. Without internal pressure, Earth would form a tiny black hole about 3 millimeters in diameter.
Why would it have a diameter? I don't know. Why wouldn't it just do a singularity? But whatever. So you could talk about a neutron star being made in a similar circumstance. So you could just stop at neutron star, but they always choose to go too far. And the only difference between, say, a neutron star and a burning sun is the fact that the neutron star emits its energy, reflects it quicker, and therefore doesn't have the same differential, therefore it isn't creating the same heat. Something like that. But it's clearly the heat that causes things to catch fire, so to speak. So if we could increase the temperature inside of Jupiter by another 1,000 degrees Kelvin, maybe it would start burning. It's that simple a truth.
And the real estate market would go to hell. But let's go back to the accelerometers to see what else they can tell us.
So it's just, now she's going to tell us it's a spring. So, like I said, when I first watched the video, I just kept saying, it's a spring.
The easiest example of an accelerometer is a spring.
There you go, right. But she's using it as an example, something that looks like a really rigid spring, right? So none of what she's going to say has anything to do with this kind of a spring. A stiff spring will not do any of the things. It's a terrible accelerometer, okay? It won't tell you anything. You need a spring that's capable of measuring the amount of minor, tiny bits of pressure differentials. So obviously you're not going to be able to measure any pressure differentials with a big hard metal stiff spring. You need a lot of pressure to create any differential. So she didn't even do this spring thing very well. She should have used like a slinky or something that would have a more obvious capacity to measure little tiny bits of difference in momentum. And clearly, the only way you make this spring mean anything is you tie a weight to the end of it. Then it really tells you the truth. But without a weight, you're just really using the weight of the spring. And it's a tiny amount of weight, so you've got a tiny difference in pressure. And that's not going to work either. So she really made a mess out of this. It's a terrible analogy when you don't make it obvious how the spring can actually do this flexing thing.
Yes, a plain boring spring. Suppose you put...
So there's no such thing. There's so many different kinds of springs. Coils. There's all kinds of different ways to arrange a stressable media, okay, that can store energy.
A spring into...
a piece of wood is a spring. Lots of things have springiness.
Outer space, empty space, flat space. How does it get there? I don't know. Maybe Bob the astronaut.
So more nonsense, more jokes. And so what would be the thing if I did have a spring in space? Let's say I made the spring really big. So what if it was a mile across? Then I could start understanding and calculating the fact that, that means it has a lot of mass. All of that mass is going to be under pressure. That is, the external universe is going to be pushing stuff together, and there's going to be all kinds of heat generated in the spring. I'm going to actually start getting 10 degrees Kelvin, 20 degrees, 30, 40, 50. It's going to start increasing the temperature of that spring because the spring is going to start collecting pressure. But in the end, it's going to get to a point of equilibrium in about a millisecond. Okay, it's going to reach equilibrium, and the amount of energy going in is going to equal the amount of energy coming out. But it can't get there. And the important fact is the energy right now it isn't going to be the same energy. It's always going to be a little bit behind.
Astronaut lost it on a spacewalk. I hear these things happen.
Whatever. Humor and science. Oh, it's just such a wonderful combination. Shit.
Okay, there's a spring in outer space for whatever reason. It'll have some extension. Now, if you tie that spring to a rocket, and that rocket...
And so what makes the rocket move? Oh, Newton's third law? You mean the momentum coming out of the exhaust will equal the momentum of the spaceship? Yeah. But no. There's a whole bunch of kinetic energy coming out of the exhaust. 1,000,000 times more energy than the momentum. And so the spaceship moves 1,000,000 times with 1,000,000 times more momentum because there's 1,000,000 times more energy coming out of the exhaust because I've squared the velocity. Erroneously, insanely, without any good reason. For absolutely no good reason, okay, you have destroyed Newton's third law and pretended, okay, that the kinetic energy of the exhaust means something. That somehow it's actually going to move the spaceship when the fact is it won't. The spaceship will go with 2 joules of energy and the exhaust will go with 2,000 joules of energy, and there won't be any sign of a third law. Because kinetic energy is a fable. Oh, that's probably a good enough place to end. We're at an hour. All right, so yeah, maybe this will be a 3-parter or something. It's okay. I mean, it's a really important subject. I mean, I'm annoyed that for the last 15 years or whatever I've been doing this, it didn't occur to me just how stupid bent space was as a theory, in the sense of not recognizing that it creates energy in the universe. And if you create real energy, you can't make it go away and turn into bent space. So all of the heat that the gravity creates has to be accounted for as free energy if you're not going to give me the conversion mechanism, the mechanism that makes the heat go away and turn into a bent space. Obviously, it's heat in, heat out. It's a heat-averse. Yeah, should I do that? Instead of push-averse. I mean, push-averse is just so good because, obviously it's not a pull-averse. And, but heat-averse is the truth. This movement is heat. All movement, whether it's a big thing or the friction, between my fingers or little tiny things moving, it doesn't matter. All movement is heat. Another just obvious thing to observe in the universe that I should have seen it. But I mean, they so bend your perspective. They turn you into such a pervert with their silly norms and their these silly axioms, and you end up believing what they say, and it's such a horrible waste of your neurons because the truth is so simple. All motion is heat. All right, anyway. Force equals momentum equals energy equals weight equals thrust equals, it's all the same thing. All right, so till the next time, and such and so forth, and the whatnot.